So we'll start today's session, and the goal of today's session is to go through a software which will help you solve your numerical problems using finite element. Okay, and I'm going to be giving this talk sitting down because I'll have to use my computer for this. And the one which we will be demonstrating to you today is FreeFEM++, and as I had informed all of you earlier in the emails, this is a free software. It's an open source software. You can either install it on your computers, or as in today's case, we are going to be solving it online. Now there are many such open source softwares, and we've chosen FreeFEM because, well, John at least is very familiar with this software. Okay, and I have also used it a little bit, not very much, but there are many out there, and there is no particular preference for any. And so we'll start with that. And the goal would be to look at the previous two problems that we had solved using finite difference. One is the Poisson problem, and the other one being the driven cavity problem. Okay, so let's go through the programs, how one would go ahead and program these simple ones. I should also add that there is a very detailed manual, about 400 plus pages manual, which is available on the website, and you can download and go through the examples. You can work on those examples, and yeah, that would be a good way to get started. So this is the problem. So del square phi is equal to rho, okay, when r is less than or equal to 1, with the boundary condition that phi equal to 0. Okay, this is the Poisson problem. Okay, what we do now is to multiply it with an arbitrary test function w throughout and integrate it over the space or over the domain. Okay, and then integrate it by parts so that you get the weak form, which is given right here. Yeah. So the first step to do in this software is to define the boundary, and that statement is given right here. So if you use the two slashes, the backslashes, those are the comment sections. So after those two double backslash comments, you can comment. So it's defined boundary, and the important thing to remember is the domain is always to the left of the boundary. You'll understand that when I go through this example. So border tells you the border of the boundary, gamma is the name that we are giving to that boundary, and t is a parameter that goes from 0 to 2 pi. Okay, and since our boundary is circular, it's going to be x is equal to cos t semicolon, y is equal to sin t semicolon, and both of them are inside this curly brackets. Okay, it's important to remember some of these syntaxes, because you'll get an error if you are missing one or more of these semicolons, sorry. So when you go from 0 to 2 pi, as you go along the boundary, as I said, the mesh will be to the left of that. So instead of that, if you had done 2 pi to 0, then you would get a mesh outside the circle, but you'll get an error because you don't have a boundary on the other side. So you're going from 0 to 2 pi, and so as you go, the mesh will be generated to your left, and you're closing the curve, so you have a domain restricted by this boundary. Okay, so that's the first statement. Next is the construction of the mesh. Okay, and we call that mesh th. Okay, mesh th. The statement is mesh th is equal to build mesh. Okay, gamma, right there, 20, with 20 points on the border. Okay, and now we are going to plot that mesh right there. Okay, we haven't specified here in this particular case what type of an element it is. By default, it is going to choose as a linear element. So you're going to get triangles with linear elements. Okay, so let's do that. So what I'm going to do next is to cut and paste these statements onto this. There. There you go. And I plot the grid right there. evaluate, and that's the mesh. So you can see the result, the plot here, and the output is given right there. One of the good things about running it online is, although you don't have line numbers here where you are inputting the lines, your text, in the output it in fact gives you the line number there. Okay, and if there is an error, it will tell you error on line number so and so, and so you can just look at this particular part of the output and then go to that particular line in your code and fix it. Okay, you can always do that. Okay, so let's look at the output. It says the mesh tells you number of triangles are 68, number of vertices are 45. It tells you the time it took to compile it, the time it took to execute it, and so on and so forth. Yeah. Okay, so now we need to solve the problem. Let's go to the next page. Yeah. Okay, I think I probably said something which was not exactly right. The element that you define, whether it's a linear element or a quadratic element and so on, it comes in the next statement. So please keep that in mind. So I thought that it comes there itself. It comes when you define the finite element space. So I apologize for that. So the next thing is to define this variable or this environment VH, which is a finite element space, on the grid TH that we have already defined. And now here you define the element, the order of the element. So it's a linear element or a quadratic element and so on and so forth. Okay, so P1 is a linear element over the mesh TH. So you define over this, so VH is this environment which is the finite element space, okay, and it's defined over the grid TH with linear elements, and for linear elements you say P1. Okay. Okay, so once we have done that, the next step is to initialize our variables. That's the unknown phi, solution for which that's the solution that we're looking for, and the test function W over that finite element space. Okay, so it's VH, and in front of that we have phi comma W semicolon. Right. Now we have to set the value of rho, and in our case we'll take it as to be a constant -1, set rho. So this is again a comment. So again it is over the same finite element space, okay, and that particular space that we have defined is VH, and so VH space rho is -1. Rho could have been a function of x or y, so you could have said rho as say x times y or whatever function that you want to choose. In our case we are going to choose a simple function which is a constant which is equal to -1. Okay. Okay, so next we come to the weak form. So once we have defined the space, we have defined the variables and all those things, now we come to the weak form of the Poisson equation with the boundary condition. Okay. Now there are two ways to do it, and the simplest way is what we are going to show you here. If there are iterations to be done or you want to find out the value in time, there's a slightly different way which we'll do it in the next problem. So we say solve, right, so that's the statement, Poisson, okay, in brackets, so we are defining this, the equation. It's a function of phi and W. Recall phi is our variable phi and W is the test function, is equal to integrate over these two dimensions, 2D. And what is that grid that we are doing it over? This is TH, okay, times d phi by dx. So the way you write it is dx in brackets you have d phi with dx with phi inside, so d phi by dx into dw by dx plus d phi by dy into dw by dy. Okay, so let me pull out the code that's there. So this is from their manual, and the reason I'm doing that is because these statements are nicely written right here so that you can see what's going on. Okay, you can see these two statements. So it's grad u dot grad v. So again here too they are integrating over this two-dimensional mesh. TH is that environment, the mesh. So you can see that it's du dx, dv dy, which is essentially this. You're integrating, that's dx dy. Right? Okay, so that's that. And then we have the second integral, write that one, because this entire thing is in the integral. So we have plus rho times w. So what you have to do is take everything to the left hand side of the equation. So the right hand side is equal to 0. Okay, so we have that second term, and so you write that second term separately. You say int 2d over the same space, rho times w, the test function. So what is very important to remember is that you do not write both of these two terms together in the same in the same statement, that is inside this bracket, because you can see this is bilinear because you have both phi and w over that space, and here it's only w which is there, the test function. So that has to be separated. They should not be in the same integral, right? That is for the coding part. Plus we have the boundary condition. On means on the boundary. Gamma, that's the definite, that's how we defined the boundary. Phi is equal to 0. Define that. Okay, that's it. We plot the result. To plot the result, we just say plot phi. So let's do that. Find out that. Okay. Thank you. VH. Right, define rho. The weak form is next. We plot. Yeah. So that's the mesh. Now, if you're solving it online, you'll only get one plot. So it's a good thing for you to just first write the statements for the mesh and then plot it, and then see whether your mesh looks right, and then continue with the rest of the statements. Okay. Okay. There you go. That's the solution. Right. Recall that we have 20 points on the boundary. Okay, and that's the plot that we have. Now we can look at how the value at some point in space varies as we change the number of points or number of elements essentially. For that we have this last statement. There. So if you look at this statement that I have here, you say that you essentially want the value of phi, so we'll pick the value at the right at the center, which is x equal to 0 and y equal to 0. So C out phi and L. Okay, end of line. So if you do that, so if you give some other value, you get the value of some other value. So let's run it again and see what the value comes out to be. It comes out to be 0.25, it's right here, 0032. I don't know if you can see that. Of course, you can get the analytical solution to this equation, which is 1/4 of 1 minus r square. So at r equal to 0, it should be 0.25, and we get a value which is very close to that. Okay, but that's a bit misleading, as we will see soon. So you expect that if I increase the number of points on the boundary and therefore increase the number of triangles, number of elements, I should get closer to the solution. Yeah. So you can see it's off by 0.000032. Sorry, right there. Okay. I forgot to mention that also it gives you the residual, the maximum and the minimum. This is initially when it starts off and right towards the end after it's done solving. So it's really small. Okay, so let's kind of remember this value. Okay, and now I had 20 points. There. And let me make it 21 and run the entire thing again. That's the contour plot, and you can see that it's much worse. Okay. Blow it up, sorry. Thank you very much. Yes, there you go. Right there. Okay. And the reason for that is because when you have elements, the point that you're choosing need not be at the vertex. Right? It could be somewhere in the middle. Okay. And therefore, the error does not go down as you expect that to go down for this. It will be close, but it doesn't go as expected for this. And so there is a statement right here in the notes that we have. So you start with 20 points, you get a certain value, but this is unrepresentatively accurate. Because with 14 points you get a different, with 28 points you get different. So it's a bit erratic depending on how close the point that you choose is to the vertex. Okay. So you could choose quadratic elements. Instead of P1 you could choose P2 and then look at how close is it to the analytical solution. So all you have to do is to go up there, change it to P2, go back to 20, right, and then evaluate. Okay, looks better right there. But interestingly, surely you get a value which is 0.245491. Okay, still not as good as what you got with P1, but again it is because probably the value of 0, 0 was very, very close to the vertex. And although you are using quadratic element there, bilinear, sorry, right, P2 is a quadratic element, I'm sorry. You are probably still away from the vertex, but with finer mesh, you can check that the error starts reducing compared to the analytical solution. Okay, so that will be probably an exercise that we will give you. Okay, then now we can try and do a few examples on boundaries. So we chose a circular boundary. Okay, by the way, this is a plot of the same solution, but I think the values were taken on a file and then plotted using gnuplot. You can check if there are similar plots that can be done on FreeFEM, I'm not sure, but since you know MATLAB and Octave now, you can always output these results and plot them on gnuplot or MATLAB or whichever is your favorite plotting software. Okay, so now let's take a look a little bit on boundaries, and so I will delete this file, go up here, and the idea is to plot an ellipse and have an elliptical boundary with an elliptical hole inside. Okay, so that's what we're going to do. Okay, so here is the program. So first we define the length of the semi-major axis and semi-minor axis. Okay, and that's the first statement right here. Hope you can all see this. I'll just expand it a little more. Again, now we define the border of our mesh. Okay, so we call that gamma, the first one, and this is going to be the outer boundary. Goes from 0 to 2 pi, and again here t is my parameter and my x and y are given here. X is equal to a times cos t semicolon, y is equal to b times sin t semicolon. Right. So that's my outer boundary. Then I define my inner boundary, which is border gamma 2. I give it a different name. Again the parameter t going from 0 to 2 pi, and I have it as 0.5 times A is equal to B 0.5 times B. Okay. Next I construct the mesh, and here is something important, mesh TH. So I am defining the mesh is equal to build the mesh, that is the command, and in the bracket you will see it is gamma 1 and I need 30 points on the boundary plus gamma 2 minus 20. So essentially the mesh, the second mesh is subtracting the mesh from the outer mesh, okay, and then we plot it. So let me copy that, there you go. I think I need a semicolon, oh, okay, I thought I need a semicolon there, and there you go, that is how it looks. So I had a minus 20 in the bracket of gamma 2, subtracts it. Okay, that's the mesh, right? And so one could in fact with this boundary go and solve the same problem. I'm not going to do that, and you can try that out. It works out very nicely. The same Poisson problem with phi equal to 0 on the boundaries, and you can see how it looks like. So you can see how easy and convenient this software is. The other thing you can do is to adapt the mesh. So you can refine it in certain regions and make it coarser in other regions. That also is very easy. So let's look at that. Okay. So as before, we define a circular domain. We mesh it with 20 points on the boundary, we plot it. So let me do that so that we can see how the mesh looks like without the refining or local refining. This is how it looks like. Okay. Next, I define this finite element space VH on the mesh TH with linear elements P1. So these are all triangular elements. I can do that next. There you go. Now what I do is I define a function f. Okay, it looks somewhat similar to MATLAB except that I don't have a TION, but it's func. F is equal to this, okay, where x and y are my variables over the mesh, over the domain. Okay, and I define this variable fh. Okay, over this space finite elements space VH, which is equal to f. Okay, and the next statement is mesh TH2. Okay, recall that the earlier mesh was TH, so now I'm making a second mesh called TH2, which is equal to, instead of saying build mesh, I say adapt mesh here, and the mesh that I'm adapting is the TH, which I've already built, comma FH. Okay. Now if you look at this variable, when x is large, greater than 0.5, and y is greater than 0.5, a certain number, when x, so why don't we look at the plot and then we come back to this, sorry. Here you go. Right. So evaluate. Okay. So what you can see here is, let me expand this. Yeah. So if you pick a number such as x equal to minus 0.8 and y equal to minus 0.8, because you have both minus minus and it's a cube of that's going to be a large number. Whereas if I picked up x equal to plus 0.8 and y equal to plus 0.8, it's going to be a smaller number in magnitude. Yeah, and so you can see the effect that this region right here is denser and this side is coarser. Okay, so we can play around a bit with that, and so let's say I just say that, I delete that. So you can see that when I deleted the y, the variation is only along x, right? And on the left hand side, because this is a large number, left hand side, denser on the left half, coarser the right half. I think it's only taking the magnitude. Am I right? Ah, okay. So very large negative is coarse. Yeah. Oh, sorry. So fine. Large negatives. Yeah. Okay. Sorry. So I think I need to correct myself. It's both the magnitude and the sign which is important, and therefore if you have a large negative value, it's very fine. A large positive value is coarse, but please try it out. That's it. Okay. Yeah. Well, you define that 20 points. I think the software does that. It calculates and then does that. It's quite possible that you could get very skewed elements, in which case it's not a good idea. So you can change the number of points on the boundary, and therefore make sure that you don't have large obtuse or acute, small acute angles. Okay. Yes. Right. So just to repeat what was said, everything is an integrated environment. You build the mesh, solve everything in here, but there is, you could build it, the mesh from outside and then import it, but you'll have to go through the mesh. Those are the finer details of this software. Here is the Navier-Stokes equation. This is the continuity equation, and we have made use of the pressure penalty formulation here. So it's del dot U is equal to minus times a very small number chosen as Timbo minus 6 times the pressure. Okay, right? And so we discretize the Navier-Stokes equation in time. Okay, it's at from n plus 1 minus n, so n is telling you the time, n plus 1 minus time. The advective term or convective term, we take values from the previous time step, whereas on the right hand side we are taking the time for the next time step, which is n plus 1. So it's an implicit formulation, and Professor Hinch is going to talk about this next week. And again we have del dot U for the next time step is equal to minus this very small number times the pressure at the next time step. Okay, so as before, you multiply with the test function, which in this case is V for the first equation and P for the second equation, and we are writing the test function V in the vectorial form. So please note, that's why it has a bold face V, and Q is not, it's a scalar. And we integrate over the domain and we reduce the high derivatives. Okay, and so if you work it out, it should come out to be this. So you can check this as an exercise. Okay, so you have U n plus 1 divided by delta t dot U dot V test function, and this term nu times gradient of U double dot gradient of V, this one comes from our viscous term right here, del square U. When you multiply it with the test function integrated over the space, minus Pn del dot V minus del dot Un Q, and then what we have done is multiplied. So the second equation, we take that and we subtract this from that. So that's why we get this minus del dot Un plus 1 times Q, so that now we have a single equation. right? And then we take everything on the left hand side, and this is what we get. Right. Slightly complicated, slightly more complicated than the previous example, but very much doable. You'll see that maybe in another 10 lines you have the entire code going. So this is the heart of your program, so the weak form. And then we would like to plot the streamlines just the way we did it for the stream function vorticity formulation that we did. Plot the streamlines. So we have del square psi is equal to minus omega. This is my minus omega. So once we solve this, we have the velocity in the x and y direction, and then we solve this to get psi. We plot psi. Is that okay? Okay, so we have that, right? Okay, so let's start with the program. So nu here is a non-dimensional form. So nu is 1 by Re. We can choose Re equal to 10. That's what done here. Number of points on the sides. So this is a square box is what we are going to choose. 20 on each side. And final time is 3 units. The number of iterations that we need to go through is 30. So these are the number of time steps to stop. So we are here interested in the final steady state solution, and so it's like a pseudo time step. We really are just stepping in time so as to get to the final steady state solution. So the delta t is this final time divided by ITT, which is 30, so 3 by 30, okay, it's 0.1, and then integer j we define, and integer I, which is equal to 0. So you can see that these ints for integers, for real variables it's real is what we use. So similar to many other programs. Next we define the boundaries. Okay, so first we define the bottom boundary, border bottom, we call it bottom, and the parameter here is t again, goes from 0 to 1. Okay, we hold y constant at y equal to 0, and x increases from 0 to 1. We call the mesh is to the left of that. So as you go along, so mesh should be to the left. So on the upper side is what you get. The right hand side again we call, so we do similar statement, we call it r side. T goes from 0 to 1, x is equal to 1, and y is equal to t. Okay, go up. So we go bottom and then the top. That's what we go. Okay. Now we have the top side, we call it top, t equal to 0 to 1, and you can see that here x is equal to 1 minus t, y equal to 1, right, because we are now on the top right hand corner and we are moving to the left this way, and that's why x is 1 minus t, right. T is equal to 0 gives you the corner, and then you have to come all the way to the left, top corner. And then similarly for the left side, once you are on the left top corner you have to go down, and so t equal to 0 to 1, x equal to 0, y is equal to 1 minus t, right. So now once we have defined the borders, we will build the mesh. The statement is mesh, th is equal to build mesh, bracket open, bottom nx, number of points on that boundary, the right hand side, the top left hand side, all 20 points everywhere, and we plot the mesh. So let's do that. There you go. That's the mesh. Good. So now that we have the mesh, we define two finite element spaces over the same mesh. One we call XH, okay, and the type of elements that we are going to use are the quadratic elements, so that's why it's P2, and we'll use it for the velocity. For the pressure, the space we'll call it as MH over the same mesh TH or the same grid, and here we are going to use linear elements. Okay, so once we have defined these two finite element spaces, XH over this space xh which we have defined, we have the variables ux and uy. Ux is the velocity along the x direction, uy is the velocity in the y direction. Vx and vy are our test functions for along the x direction and y direction, and ux old and uy old are the velocities, the old velocities, old time velocities. Remember that we are time stepping, we have something at n plus 1 and something at n. So n plus 1 are this ux and uy. At n, which is the older time step, we have the ux old and uy old. Okay, so that takes care of the velocities. Now for the pressure, P is the pressure and the text function is Q. Okay. So once we have done that, come to the weak form, and you see that's slightly different from the way we solve the Poisson problem. There we just said solve, but here we need to iterate, and so we say problem, okay, and the name of that problem is NS for Navier-Stokes, and the round bracket opens, and in square bracket we are defining the three variables ux, uy and p, square bracket close, and then in the second square bracket we have the corresponding test functions vx, vy and q. Okay, we choose a solver. There are different types of solvers, so we have chosen a certain solver right here, and we initialize I. Init is equal to I, there, bracket. So the idea is we are going to iterate this. Okay, sorry, so we don't initialize here, sorry, this is the integer I, am I right? This is the integer I, init I.
So if you put that statement in,
Yes.
iterate, it doesn't recalculate the stiffness matrix every
Ah, right. Okay, so that's important. So once you say it's right here, in fact, in this statement, when init is equal to I, is to store the stiffness matrix and not to recompute it. Thank you. And that is equal to this, which is the weak form. You're integrating it over the same 2D domain, and these are all the statements or the lines that come from the derivation of the weak form. Okay. Again, here wherever you are multiplying a weak form with the variable right there, okay, so here you have a dvx by dx and you have dvy by dy, that comes in a different integral, okay, whereas the old values you're taking is from the previous time step come in a separate integral right here, because you have already solved for those, you're not solving for that you take from the previous time step. That's what it is. Okay, and now we have to define the boundary condition. So this is a driven cavity flow, so we have a different boundary condition on the top compared to what's there on the other three sides. So on the top you have ux is equal to sine pi x times sine square pi x, that's what the statement is right here, and uy is 0. On the other sides, left, bottom and right hand side, is ux equals to 0 and uy is equal to 0. Yeah. So now you have defined the problem ns, okay, and here is a loop where I goes from 0, okay, till ITT. This is the number of steps that we have, and I plus plus, so this is like a C plus plus or C kind of syntax, and this is the loop where you say ux old is equal to ux, uy old equal to uy, and then you solve. Okay, so you initialize the values, these are 0 initially, you solve, you go through this integral once, solve that, okay, and then when you come here, my ux old is ux, uy old is uy, and then when it solves, it calculates the new values of ux and uy and also takes this ux old and ui old in this integral. Right. So once you're done with that, we calculate the force at each time step. Okay. and that's there in the next statement right here. This is a comment, C out at t is equal to whatever the value dt times I. We know what the value dt is, and force is equal to init 1d th top, and here is du, so it's dux by dy. Yes, that's what it is. Right? Okay. So let's solve this. I cut that and I paste it, except for the fact I have an extra here. Right. And I evaluate. It's done that. So you can see at each time, I'll expand this. So when I do that, it tells you the number of triangles, number of vertices. It tells you the force at each time, 0.4, 0.2, 0.3. It's calculating the force. Keep going down. 3.89, and you can see it's converging. 2.1, 2.2, 2.4. You can see it's converging very slowly, and so that's the force at the end of your simulation, t equal to 3. So it tells you the time required to compile, time required to execute, and so on. If you do it on your own computer, I'm sure it will be much faster. Okay, now we'd like to plot the streamlines. Let's do that. Oh, so the one more thing before we go to that, and that's something that you cannot do on the online version, is to plot, to save the point. So let's say if you want to know what the velocity is, the horizontal velocity, let's say along the center line, and that's the statement that's given here. It's the output file of horizontal velocity on center line. It's x equal to 0.5. And the statement for that is here, off stream O file, the name of the file is rest.txt, okay. And now you open a loop for j equal to 0, j less than 51, increment by 1, x equal to 0.5, and you're going along the center, y is j times 0.02 because that's the spacing that you asked for, and you can output all of that into this file rest.txt. First y, give a space, and then ux. Similarly, you can get ux, uy, anything. Sorry? Right, so what you're saying that, okay, so I should write this entire thing also on the online version. Oh, that's very nice. Okay, good, thank you. Okay, so I do that. There you go. And then what do I do? Which command? Comma append. That's it. Oh, very good. So let's see. I didn't know this. Right. And where is the file? Is it right here? Oh, that was the point that I was saying, that on the online version you can't save the file, is what I was trying to say. Yeah, we can't open. Yeah, you can. So yeah, well, because you're running this on their computers, right? Well, the other way is just to output it, to get the output on the screen, copy it, and then copy to your file, open another text editor, paste it, and then do that. Okay, good. Right, so stream function. Now we would like to plot the stream function, find stream function. So on the same space xh, let's go back, find a little space right here. Right. Now I define my stream function psi, and this is the corresponding test function. Okay, so let's do that. There, and I will, so I know that you cannot see this, so just please bear with me. There you go, and I will zoom it. There you go. Alright, so I have now on the same finite element space, I define these two variables psi and w. Then as before, I say solve streamlines. The input variables are psi and w is equal to, we integrate. So again we get the weak form of this equation. So multiply both sides with w, integrate over surface, okay, integrate so that you reduce one order of derivative, and that's what you have. Again, take everything to the left hand side, okay, so you get these two integrals, and then you define what the boundary condition is, top, left hand side, bottom, right hand side, and so on. Okay, so I do that, and then we can plot. Right, hopefully it works. Yeah, there you go. So what I would recommend is that there are lots of examples that are there in the in this document, the user's manual. There are lots of different examples, heat transfer and so on, and it's a good idea to, in fact, so if you seriously want to use this for your research, something, it's nice to go through those examples, then so that you can familiarize yourself with all the various variables. So the idea here is just to let you know that there is this software that exists, and it's very convenient. You can solve very complicated problems, it appears, quite simply, not with many statements. Okay, thank you very much.